In this problem, we are given a surface integral that is computationally difficult to compute, to find, and we want to basically use divergence theorem to break it down into a triple integral and another surface integral. So let's start with it. First of all, it's asking you a compressible, that's the opposite of incompressible. Fluid is flowing through a net. And the whole point of this is that fluids are typically considered to have divergence equal to 0. We're just saying, well, imagine this is a fluid that doesn't have divergence equal to 0. It's flowing through a net described by equation. An equation is given here. Let me think what this is. If I go to power 2 for this, it's going to be z squared equal to 9 minus x squared minus y squared. Remember, z has to be bigger than equal to 0 because of the square root. And then take all the variable on one side, and you get this, which is a sphere of radius 3. But because z is bigger than equal to 0, it's just some hemisphere. So it looks like that, basically, almost this. And so it's just a hemisphere, and it's telling you that it's oriented in positive z direction. So it goes like that. The normal vector, the unit normal vector, is outward that direction. So my first instinct is, well, they are asking determine the flow rate of the fluid across the net if the velocity vector field for the fluid is given by this vector field. Find the vector surface integral, right? That. And my first instinct is always is to parameterize the surface and compute everything. And parameterization of the surface is not too bad. I'm just going to use the spherical coordinate to easily do this. And z equal to 3. Oh, I'm sorry, that was an error. Cosine phi. And then I can find n, and n is going to be and n, as usual, is going to be equal to, I can either do I, j, k, and a plus a minus, and compute if this is, let's say, g. I can compute g plus or minus of g sub phi cross g, or g sub theta cross g sub phi. And that is just the computational wise, we should never try this because it's very time consuming. And we also have other knowledge that makes our computation a lot easier. And 0, and then I have 3 cosine theta, cosine phi, 3 sine theta, this one is 3 sine theta, derivative of that, cosine phi, and here negative 3 sine of phi. And I know n is the outward direction, and that's the good direction, and I just can put in the Jacobian in here without computing it, which is the radius 9 sine of phi times the little n. The little n, I have to convert it to spherical, and again we computed this multiple times. It's just going to be cosine theta, sine phi, sine theta, sine phi, and cosine phi. Now the next step that I need to take is to compute f of g, and that ends up to be sine of 3 sine theta sine phi to power 2, and natural log of 3 sine theta sine cosine, oh sorry, this one is x, so 3 cosine theta sine phi to power 2 plus 1, and then 3 cosine phi. Dot this, take the integral. This is way too messy. Is there any other way that I can do this? Dotting this is just writing it up is very long. So one way that people basically helps figure things out is this. Let's go back down. Let's say this is the hemisphere. Hemisphere is not a closed surface, so there is no volume involved in it. But if I cap it off with the big disk on the bottom, that's the disk, let's say in XY plane, that's this disk that you can see right here. What is that disk? Let's compute it really briefly. I know that it's the circle around the disk is just a circle that is intersection of these, the sphere with the z equal to 0, which is just x squared plus y squared equal to 9, and therefore the disk is can be parameterized. Let's parameterize this quickly by radius changes between 0 and 3, so r cosine theta, r sine theta, and z was supposed to be 0. And so let's cap it off with this surface. Now, by divergence theorem, let's say this was S, and let's call this one S nu, right? So S and S nu together create a closed surface, piecewise defined, but it's okay. And so what I do is I put in outward direction, and in that way is outward already. And the outward direction for this surface, let me think about it. The surface is basically the bottom part of the sitting on the XY plane right here, and therefore the normal vector out that is just negative k, the unit normal vector. So that's the by divergence theorem I can say, now let's say there is a volume W, which is the inside the hemisphere capped at the z-axis. Let's say there's a volume W, and the divergence theorem says that the divergence of f, the triple integral of divergence of f on that W is going to be equal to the surface integral of f on S plus the surface integral on S nu of f. Okay, these two are still surface integral. That one is just the, basically you can see a triple integral. It involves sphere. It's just a spherical triple integral, a triple integral in spherical. I think we had it in section 15.4. And it's relatively simple, not computationally difficult, spherical integral. Let me think. So what I need to do, this is what I want. I have to compute this, and I have to compute this, and then solve for what I want, basically. To compute the surface integral on the new surface, I have to do all the process of the surface integral. So the first thing that I want to do is I find n, which is the, again, plus minus h sub r cross h sub theta. I can again do the entire shenanigan, or I can remember how it goes, basically. Cosine theta, this with respect to r, this with respect to r is sine theta, and 0, then that with respect to theta, and that with respect to theta is this. If you compute it and simplify, simplification again is very important. You get r, and instead of plus and minus, I just decide what I'm going to, oh, sorry, r doesn't have the arrow on top. I will get r times the negative k. So let's go back. I know I need to find f of h and then dot it by the capital N. So let's go back and figure out what f was. F, because I'm dotting it with negative k, the only z value is important to me. So I can even write it as something, something, and z dot n. And I know parameterizing z was equal to 0. Where is h? H here. So it's not really that. It's just this. And this is going to be 0. So the first thing that I needed to compute is going to be just a triple integral of, this is going to be, surface integral of 0. So this is going to be equal to 0. All I need to do is to find the divergence of f, and then do a triple integral, basically. So let's go back. What is divergence of f? Divergence of f is equal to partial respect to x of sine of y squared plus partial, it's a dot product, right? It's the div is the dot product. Partial with respect to y of natural log of x squared plus 1 plus partial respect to z of z, and then you end up at 0, 0, and 1. So divergence of f is 1, and let's do the triple integral now. And the triple integral, and the integrand is 1. I want to do spherical, so what I'm not supposed to forget is rho squared sine of phi, which is the Jacobian. And then I will have d rho, d phi, d theta. And rho runs from 0 to 3. Phi starts from here, which is 0, goes to the xy plane, 0 to pi half. Theta goes from 0 to 2 pi. And let's do the integral. Rho becomes rho to cube over 3. And from 0 to 3, right? And then I have 0 to pi half, 0 to 2 pi. And then times sine of phi, d phi, d theta. And what else do I get? I get here 3 to the power 3 is 27 divided by 3 minus 0 is going to be 9. And so I have 9 sine of phi and 9 sine of phi. Let's take the integral 0 to pi half d phi d theta 0 to 2 pi, and that gives me 9 cosine of phi negative 9 cosine of phi 0 to 2 pi half, and integral from 0 to 2 pi d theta. So cosine of phi at pi, let's write this down. Cosine of, we have so what we need to do is write minus 9 cosine of pi half, that we know is equal to 0, and then minus 9, which is plus 9 cosine of 0, which I know is 1, and then compute integral from 0 to 2 pi of that over theta. And so the final answer in here is going to be, wait, that one was 9, and so with respect to theta I get 2 pi times 9, which is 18 pi. Now this is the triple integral of the divergence. This was the divergence right here that we computed. Now going back up here, I can see that this is what we computed, and that's 18 pi, and this other alternative surface integral was 0, and the sum of the two surface integral is supposed to be 18 pi, so the surface integral f dot ds on the original surface is going to be 18 pi.